So use this equation to calculate out the primer binding temperature, so-called annealing temperature, right? So to count the number of G's and C's found in your primer sequence and times 4, plus count the number of A's and T's found from your primer sequence times 2. And if you add them up, actually that is the melting temperature where your primer is not going to bind, but minus 5 degrees Celsius is going to be the binding temperature. So not far away from the melting temperature, but 5 degrees away. So that's good, because if it's too low, then you will have a lot of force priming happening, which is not good either. So normally the temperature is between 50 and 55 degrees Celsius. That's the primer binding temperature. And then the factors that can affect the polymerization of your replicated product. So you're going to add dideoxynucleotide in your reaction, sequencing reaction, right? So it depends on how much your dideoxynucleotide you add. What is the ratio between the dideoxynucleotide you add and the normal deoxynucleotide? That determines how frequently your replicated product will be terminated. Okay, so if you want to intentionally terminate your replication early so you can get the sequence information very close to your primer end, yeah, then you can add more dideoxynucleotide than normal. Okay, so the normal ratio between dideoxynucleotide and the normal nucleotide is about 1 to every 99. So it's like a 1 to 100 ratio. Okay, but you can add more dideoxynucleotide and it will be more frequently terminated. Then it will be easier for you to identify the sequence close to primer. Okay, that's what it means. Okay, that makes sense, right? Also, if the template has a unique nucleotide that's more happening frequently, you need to consider that when you add nucleotide, so it doesn't run out during the replication process. That also makes sense, right? And then I already talked about these issues. If you have a lot of secondary structures on your template DNA or maybe the replicated DNA, you will have these problems. For example, compression is due to the fact that your replicated product has secondary structure. So when they are separated on a gel, electrophoresis, you see the overlapping of the two dideoxynucleotide. You know, one will be true and the other is fake because maybe the other maybe have the secondary structure showing up, so they are ending up on the same location on the gel. Then you don't know which one is true, which one is false, right? So that's a kind of complicated issue. You can identify what the true nucleotide sequence is on the place like this or maybe place like that, right? So that's a compression issue if there's a secondary structure problem happening on your replicated product. Then how do you solve that? You know, these are the suggestions if you have the problem. Back in the older days when you run your electrophoresis gel, you know, slab gel, you're making the gel, you run it, you can increase the, denaturing condition by adding more urea or by running the gel in a higher temperature condition. Okay, that could be a possible solution. Okay. So by adding those conditions, you can denature the secondary structure on your replicated product, so they can be really sorted out based on their true sizes. Okay, so that could solve, but it depends. Another solution would be you would use something like this. This is a nucleotide analog, so deoxy ITP. Okay, so this has a very similar structure as GTP, right? So if you compare their structures, they are very similar. The difference is, so amino group there, there's no amino group there, right? So actually ITP can be added instead of GTP, okay, and the replication can take place. This is a, deoxyribonucleotide, so you can continue the replication. So G's can be replaced with I's in your sequence reaction. Then what's the benefit of that? The benefit is, GTP can make those triple hydrogen bonds with the C's, right? G's, C's makes the triple hydrogen bonds. So those will create that secondary structure problem. But this one, ITP, doesn't form the triple hydrogen bond. So ITP would not make you a lot of secondary structure problems. So that's why they are suggested to add maybe ITP. Its name is deoxyinosine 5-triphosphate. So replace GTP with ITP, then you will resolve that secondary structure problem. So that's a solution to that problem. Okay. And the premature termination, I already talked about that. If you have a strong secondary structure on your template DNA polymerase can run through that, you're going to have a termination of the polymerization. Then you cannot read any sequencing because you don't have the replicated product. So that's a problem, right? So then how are you going to solve that? So solution is add more polymerase, DNA polymerase, see if we can run through that area, or do the replication at the higher temperature with Taq polymerase. Taq polymerase is what? Heat resistant DNA polymerase, right? It can run at 74 degrees Celsius. Yes, if the 74 degrees Celsius is high enough temperature, it can get rid of those hydrogen bonds on your template DNA. Yeah, definitely it'll work. So use Taq polymerase and do the replication at higher temperature. Then you'll get rid of the secondary structure problem. These are kind of possible solutions to that. And then contamination issue on your template DNA. Like I said, you should use a very clean template DNA for your sequencing. Otherwise, you have very strange result. Polymerization is not going to work. So contaminated plasmid DNA preparation will lead to the overlapping peaks. So there may be some peaks overlapping like this. Okay, because the primer is binding on the normal target template DNA, but there's another background DNA and your primer may bind, so there's a background peak may show up. That's a problem, right? So sequence data is cleared out to the end of the insert cloning site. So you have to clear up your template DNA. So that's the solution. So, and if it's contaminated with another DNA, you may have to go back to the original clone and get a pure DNA and start it over. So that's the suggestion for that issue. And high background. See, there are so much peaks. There are so many background peaks, which is not good. So low or poor signal or too much noise in the background. That's caused due to too little DNA template is added, because the primers don't know what to do. It's just randomly binds and it randomly creates the products. That's the reason. So primer binding to the template that is not efficient. So there may be a random priming happening. Okay, so not enough terminator mix was added. So dideoxynucleotide is not enough. It's not terminating on the right side. That could be the issue. Okay, so the DNA template was not purified. It's dirty. So all these possibilities will cause these high background problems. And how are you going to solve it? Solution is increase the amount of template DNA, of course, increase the amount of primer in the reaction, okay, or increase the amount of dideoxynucleotide, and prepare the DNA again so it can be clean again. So those are the suggestions if you have those. No readable data. So if you have this junk, well, what kind of peak do you see? It's just gibberish. You cannot identify what they are. And it's due to maybe lack of sequencing data. There is much sequencing happening, and sequencing trace is non-uniform. Okay, and primer is not annealed to template. If you don't have a primer that's not binding on the template DNA, yeah, you will see something like that. No DNA template present in the sequencing reaction. You don't have enough template DNA, then you're going to see something like that either, because primer will bind themselves. And incorrect cycling of the sequencing condition. If you're using PCR, maybe your thermal cycle was not generated correct, and temperature is not denaturing the template DNA. So during the cycle, and template DNA is very poor quality. So all those reasons can cause these non-readable data gibberish. Then what's the suggestion for that? So design a new primer so it can bind better. Okay, and then if possible to verify DNA sequence before addition to the sequencing reaction, DNA concentration, to make sure that you have enough of it. So you can do the UV 260 and 280 at that reading to quantify it. Use the correct amount, of course. Verify that your cycle sequencing conditions are good, and the primer binding condition is good, amplification condition is good, denaturation condition is good, all those things. And then incubate your sequencing reaction at 96 degrees for 10 minutes. Denaturate, long denaturation. If the denaturation was not good enough, so primer is not binding, that's the suggestion. Okay, so these are all possible suggestions. All right, I hope you learned a lot about the DNA sequencing. Okay, so that's the end of the lecture 10.